Hi, welcome to our very first vlog. My name is Delaney, and I will be starting out this analysis of our observation. Just want to point out that this will look a little bit different from other vlogs. I will do a little bit of a slideshow to show different images and aspects about what I'll be talking, to show some visual representation so you guys can follow along. And I just want to point out that also as it's broken down, this will just primarily focus on the introduction of this observation, not necessarily the images that we created and other aspects. So I just want to kick us off by stating that throughout the semester, we have observed and analyzed the moon, stars, and different planets. We have even observed different regions through the radio wavelengths, but now, to have one last good round off to our series of observations, we're going to talk about Messier 94, otherwise known as Croc's Eye. And just to play on words, it unfortunately is not this picture I have displayed right here, but it will be presented in the next slide. So as you can see in this slide, this is what Messier 94, or otherwise known as Croc's Eye, or NGC 4637, appears to look. I just want to note that this image was not created by my group. This is a picture taken offline from Wikipedia. This will just give you kind of an idea of what the region looks like before we go into depth in this introduction section. And maybe for yourself, you can see if this appears to look as a Croc's Eye. But I just want to note that this galaxy is located in the mid-northern Canis Venatici, and that's roughly about 16 million light years away. A few other things is that Croc's Eye is listed as a starburst galaxy, which means that the rate of star formation is very high in comparison to others. And where this high rate of star formation occurs is considered to be within the starburst ring. On this slide, you are able to see a more zoomed in image of the Croc's Eye galaxy. You're able to see more of the starburst ring and where this formation occurs. And I just want to note that most starburst galaxies seem to be caused by collisions or near passes with other galaxies, and these interactions push the gas in the galaxy towards the center where it reaches a sufficient density to cause star formation. And this type of galaxy appears to not emit more light than any other type of galaxy, but that is due to the star formation occurring in dense clouds of gas and dust, which is absorbed by visible light, and then it results in the increase of emission of infrared. And that kind of explains why starburst galaxies are known to have some of the brightest infrared objects in the universe. Now that we have learned some facts about Croc's Eye and the type of galaxy it is, let's explore some details about this observation. So first off, to capture the observation in general, we decided to utilize the Prompt USA SK telescope that is located at the Sleaford Observatory, that is also located in Saskatchewan, Canada. A few other details about the observation that my group placed on Skynet about Croc's Eye is depicted on this page. There's a few different images that depict different information, such as the exposure length, the different types of filters used, the target tracking, and the other things such as RN declination. But first off, let's note that on the left-hand side, the image titled Exposures depicts the 5 different images that were received back from the Prompt telescope. On here you can see that we decided to use the B, V, and R filters along with the narrowband filters of H alpha and luminance, and the whole intent was to help bring out some more of the natural colors in Croc's Eye, along with the gas and the dust that's dispersed throughout the region. On the right hand side, there's 2 different groups of images. The first one is titled Observation Information. It again lists the target of our observation. It also lists the telescope and target tracking. And below is the same kind of concept, such as our target, again, Croc's eye, and the RA of 1250, the declination of 4107, and the surface brightness of 13. And I also want to note that circling back to the left-hand side of the screen, you will also be able to see the exposure length of each of the images that we received back, such as with H alpha, it had the longest exposure length of about 300 seconds. Then the B filter had about 80 seconds. The V filter had about 60 seconds. R filter had about 40 seconds, and the luminance filter had about 20. A crucial part of this observation that I do need to mention is that after receiving back the observations, we noticed that we only received back 5 different images, and we were definitely expecting to have a few more images for each filter to create a stack and to further align the images together. And after transporting the images from where we received them on Skynet to our workbench in Afterglow, where we stack and align and color the images, we noticed that there was not a total observing time for each filter, which is normally calculated in Afterglow. And this is because there was some technical difficulties with the observation itself. And after exploring and talking to our teacher and TA, we were able to understand that there just was not enough images and not enough stars to be able to make a RA and declination map, hence why we were unable to use these images to make stacks, and why a lot of the information about the observation itself are not recorded. So, as mentioned in the previous slide, due to not being able to move forth with the Croc's eye observation collected from the Prompt Telescope, we opted to use another group's observation with their consent. So we were able to secure the observations from Alyssa Manis's group, which is also a starburst galaxy known as Black's Eye, or also Messier 64. This observation included the layers of B, V, R, and luminance, and the total observing time for the B filter was 1500 seconds. For the V filter, it was 701 seconds. For the R filter, it was 396 seconds, and for the luminance filter, it was 257 seconds.